Welcome back to the deep dive. Today, we're going way beyond the surface, beyond the cloud, and right down to the concrete level. We're looking at the foundational architecture of how things connect. We're mapping the network jungle.
That's a good way to put it.
Our sources today are focused, really laser focused, on network topologies. And for anyone who needs that, that quick fluency in network architecture, this is the blueprint.
He really is.
Think of it as the ultimate org chart for all your technology. It's the visual map that defines how everything is interconnected.
And that visual map is, it's incredibly powerful. At its core, network topology is just how we understand either the physical layout or, the logical structure of a computer network.
So it's about two things, right? The actual device locations and then the cables connecting them.
Exactly. Where are the boxes and what path do the wires take? Now, you might be asking, why should I care about these maps?
Right. Why spend time on this?
The major benefit, and this is critical for any kind of IT strategy, is for impact assessment. If you know the topology, you can instantly see which other device or even an entire segment is going to be affected if one device fails.
Ah, so it's a tool for foresight.
It's pure foresight. It's about troubleshooting and planning, not just a pretty diagram.
Okay, so our mission today is to unpack the two fundamental ways we look at these maps, the physical versus the logical, and then walk through the geometry of common structures. We're going to look at the trade-offs, for reliability, cost, and efficiency. Let's start with that essential divide then. Topology is split into two types. When an engineer starts drawing one of these maps, how do they decide if they're looking at the physical or the logical view?
It really boils down to one question. Do you care more about copper and concrete or packets and protocols?
Okay.
The physical topology, that's the map of the exact real-world locations. It's the literal drawing of where the devices are and the specific winding paths the cables take. This is what we call the layer 1 view.
The ground truth.
The ground truth. So, for example, if you have device A talking to device B, and the cable physically runs through a closet where there's a little switch, we'll call it device C, the device C has to be on the physical map.
Even if it does nothing.
Even if it's just a passive repeater, it represents the actual wiring infrastructure, period.
That makes perfect sense. It's the floor plan for the building. So the counterpoint, the logical topology, that must be where we throw the floor plan out the window.
That's a perfect way to put it. It throws it out the window. Logical topology is a much higher level view. It's less concerned with gravity or distance. It's focused purely on the data flow path, the layer 2 or layer 3 view.
So back to that example with device C in the closet.
Right. So if data goes from A to B through device C, but C has absolutely no effect on the data's route, it doesn't change anything important,
Yeah.
It might not even be included in the logical diagram.
I see.
The path of the data is what's emphasized over the physical placement. You're mapping the rules of traffic, not the location of the asphalt.
Physical maps the structure for the maintenance crew. Logical maps the traffic for the network admin. Okay. Now let's get into the shapes. We'll start with the two classics, ring topology and star topology.
The ring is it's beautifully simple. It works in a closed loop. Every node is connected only to the two nodes right beside it.
And the data just goes around in a circle.
In one specific direction. Yeah.
Yeah.
It travels around the ring until it gets where it's going. And a key trait here is that every single node acts as a repeater. It regenerates the signal.
So the signal stays strong over long distances.
Incredibly strong. And access is often controlled by something called token passing, which prevents data collisions. But there's a big trade-off. Zero hierarchy. Everyone's a peer.
That sounds super orderly, no traffic jams.
Right.
But wait, if one node or even one cable breaks in that ring,
The whole thing goes down.
the entire loop is broken.
That is the catastrophic risk of a standard ring.
Yeah.
It's robust against signal decay, but it's incredibly vulnerable to a single point of failure. Plus, adding a new device means you have to physically break the loop to insert it.
Which is why we don't see it much in modern networks that are always growing.
Exactly. It's just not practical for scaling.
Okay, which brings us to its opposite, the star topology. Our source material notes this is one of the most common, probably because it's so intuitive.
It is. The star is defined entirely by its single central point,
Yeah.
usually a switch or a hub. Every single device connects directly back to that one central point.
So all communication has to pass through that nexus.
It has to. And that's why it's so common. It's really easy to manage and scale. You want to add a new computer, just plug it into the switch. Nobody else is disrupted.
Wait a minute, though. We just said the ring fails because one broken cable takes down the loop. But with the star, that central switch is a mandatory choke point. If that switch dies, isn't the entire network immediately dead?
It is.
Isn't that an even worse single point of failure risk?
It's a critical trade-off. You're absolutely right. While a peripheral node failing in a star only affects itself, the failure of that central switch is catastrophic. It takes down the whole segment.
So you're trading one kind of risk for another.
You're sacrificing network-wide redundancy for the massive benefits of simple, centralized management and troubleshooting. It's just a choice you have to make.
Let's move to the most connected shape. Mesh topology. The name itself just sounds reliable.
Mesh is the definition of reliability. It's all about high connectivity. There's no central node, and devices can be directly connected to many others. It's the gold standard when uptime is everything.
But the sources were clear on this. It's not for large networks.
Emphatically not, and that's purely because of the cost. The sheer amount of cabling and the number of network cards you'd need just becomes, well, completely untenable.
And we've got two flavors here, full mesh and partial mesh. What's the real-world difference?
So full mesh is the absolute extreme, maximum connectivity. Every single node is connected directly to all other nodes.
Every single one.
Separately. If you have 5 devices, device 1 needs 4 separate cables. If you have 50 devices, it needs 49.
That's a lot of cables.
It's an incredible amount, but gives you that ultimate reliability. If 3 different paths fail between 2 nodes, there's probably a 4th one that still works. You see this in, critical military or financial networks, where cost is no object.
And partial mesh is the practical compromise, I'm guessing?
That's it exactly. In partial mesh, not everyone is connected to everyone else, so the critical devices are highly interconnected. Your main servers, your backbone routers.
So you still get the main benefit, those alternate redundant paths, without the insane cost.
Precisely. It's the real-world standard for reliable network backbones.
Okay, let's shift gears completely. Let's talk linearity with the bus topology. This just sounds like a single shared highway.
That is the perfect analogy. All the nodes are just located along one common line, the backbone cable, and data just moves up and down that line.
So like the ring, no hierarchy.
None at all. There's no central controller, which means no transmission priority. Every device essentially shouts its data onto that shared wire.
And if everyone is shouting on the same line, that must create a ton of collisions, right?
Absolutely. The defining operational detail of a bus is that every node hears every single transmission. So when 2 try to talk at once, you get a data collision. That's why it scales so poorly.
It gets overwhelmed fast.
Very fast. And here's another fascinating detail about it. Bus networks need terminators at both ends of the main cable.
Terminators?
The little caps, basically. They absorb the signal. If you forget to put a terminator on one end, the signal just bounces back and forth forever and paralyzes the entire network. Instantly.
Wow, so it's not just the traffic jams. A simple physical mistake, like a missing cap, can bring the whole thing down.
The operational risk is huge.
Okay, let's wrap up our geometry lesson with the 2 bookends. The absolute simplest and the most complex hybrid.
The simplest, without a doubt, is point-to-point topology. It's the elemental unit of connectivity.
Just 2 nodes connected together.
That's it, a dedicated link, a digital bridge between 2 spots. It sounds trivial, but it's fundamental. Even a complex mesh network is just made up of many, many point-to-point links.
Like a direct cable between 2 computers or a phone call.
Perfect examples. And finally, the architect solution, the hierarchical one, tree topology.
The hybrid.
It's a hybrid designed for scale. It's formed by taking multiple star networks and connecting their central hubs to a main central bus backbone.
Oh, so you're plugging stars into a bus.
You are. And that immediately creates a natural hierarchy. You get a root node, branches, tiers. It's great for segmentation, too. If one star cluster 1 branch fails, the main bus and the other branches are fine.
And each node can have subnodes, so it just keeps growing.
Exactly. It's why it's so common for large campus networks or big corporate structures.
So let's pull this all together. What does this all mean? We've covered a whole spectrum of choices. We've seen everything from the basic point-to-point link to the risky but efficient star, the orderly but fragile ring, and the super redundant but costly mesh.
And we finished with the tree, the ultimate hybrid, built for scaling things up.
Right.
And understanding these maps, these topologies, is really the first step in seeing a network clearly. You're defining the geometry of it all. But, and this is important, topology only describes the static structure, the layout.
The roads and the intersections.
That's right. The source material is very clear that the next level of understanding is, well, it's about how the data actually moves and follows a set of rules within that structure.
It's the difference between having the highway map and knowing the actual rules of the road.
That's it.
Which brings us to our final provocative thought for you to chew on. If topology shows us the static roadmap of the network, what invisible, structured set of laws controls the actual step-by-step traffic rules, the addressing, the error checking for every single piece of data moving between those nodes? That invisible rulebook is the next step, and it dictates everything. Go find out what it is.